In this lesson, I will talk about right triangle trigonometry. The objectives of this lesson are evaluating trig functions of acute angles and using calculator to evaluate trig functions, and then using fundamental trigonometric identities. So we first introduced trig functions from a right triangle perspective. So previously we talked about how trigonometric functions are formed on a coordinate plane, and thinking of these functions on a unit circle, and how we could, based on the given point on a circle, how we could find and define these functions. But here we're going to do something a little bit different, a little bit more geometric rather than just more coordinate based. So here we're going to consider a right triangle with one acute angle that is generally going to have some kind of label like theta, and we're going to determine relative to that angle theta, we're going to have the three sides of the triangle to be hypotenuse, opposite, and adjacent. So we use different language. So previously we used a language that we called vertical distance. You may remember that. So we called this to be vertical distance, which always represented y. And then we, instead of side adjacent, we used horizontal distance, and that generally represented x for the angle. And then hypotenuse is basically the between vertex and that point. So hypotenuse in our previous cases were always the radius, right? On the unit circle, when we had things like these, where we had a circle, unit circle, a point x comma y, we had this distance to be r, and then this one to be y, the vertical distance, and then this guy was my x, because that was the horizontal distance. And then I had my theta right here. So in this case, now what I'm basically doing is I'm creating a more generic right triangle, and then use a little bit different language. I use hypotenuse, side opposite, and side adjacent. So using the lengths of these three sides, we can actually form 6 ratios that define the trig functions. All right, so what I want you to pay attention is ratio, okay? So we can always come up with a ratio using an angle, and that ratio always stays the same. It's always the same ratio. So then the way we're going to form all these functions is going to be as following. For an angle that is in between 0 and 90 degrees, that's what acute angle means, and realize that theta is always in the first quadrant. And that for such angles, the value of each trig function is always positive. So then the way we're going to define all this is given in the table, where we're going to define sine function to be always opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent, cosecant hypotenuse over opposite, secant hypotenuse over adjacent, and cotangent adjacent over opposite. So using all this, we're going to be able to define all these trig functions. Again, the idea is very similar to what we learned before, but now we're kind of making it more abstract. We're using this concept of generic right triangle. So here's an example, and in this example, you're going to see how I'm going to use right triangle and how that is useful. So the problem says use the triangle given to find the values of the 6 trig functions of theta. So I don't exactly know what theta is, but I should be able to find all the values for the 6 trig functions. So then theta, opposite of theta is right here. The side length is the opposite, and then 3 is the adjacent side, and then what I don't know is the hypotenuse, right? So how do I find that? Because this thing is a right triangle, because I know that there's this angle that basically represents 90 degrees. And so what I'm going to do is I'm going to use the Pythagorean theorem and then compute that hypotenuse. The way I do that, I square the sides and then take the root of that, and then that gives me 5. Then the hypotenuse must be 5. And this is a special right triangle that you may have heard before, 3, 4, 5. It's always the same ratio. So then I'm going to write out all the 6. So sine is always opposite over hypotenuse. Because the opposite is 4, hypotenuse is 5, it'll be 4 over 5. So similarly, all the other ones you can essentially find by just looking at this right triangle. So I'm not going to talk all the others. You will be able to figure all the others. What I'm going to point out here is that, again, using a generic right triangle, we can always solve trig functions, and then we will be able to find values for each. So next thing I'm going to do is often I'm going to say that in general, we will be asked to find trig functions of a given acute angle. So to do this, we generally construct the right triangle having theta as one of its angles. And then these are kind of like special angles that are used a lot in mathematics. And we provide that table, and this table is generally very helpful when finding problems. So sine 30 is generally 1 over 2, sine 45 is square root of 2 over 2, sine 60 is square root of 3 over 2. Cosine is given all these values, tangent you are always going to be given. So one thing to note here is that we realize that some of the values are the same. So like we realize that sine 30 is 1 over 2 happens to be the same thing as cosine 60, which is also 1 over 2. Or sine 45 and cosine 45 have the same value, right? So there's these kinds of similarities. So what I'm going to do is that because we know that 30 degrees and 60 degrees are complementary, that thing occurs. And so what we're going to do is, in general, we can show the right triangle definitions that cofunctions of complementary angles are generally going to be equal. When we say cofunctions, we're going to say sine and cosine, tangent and cotangent, secant and cosecant. Those are cofunctions. And so generally then, what we can say is that for any given theta, then cosine of that angle is always going to be the sine of its complementary angle. So this guy, 90 minus theta, is the complementary of theta. So the sine of this is going to be equal to cosine of that, or vice versa, right? Cosine of the complementary will be sine of theta. So it's always going to work kind of like what I give here. So two scenarios. Same thing for tangent, for cotangent. They are the co-functions. So this is always going to be true. And then secant and cosecant. Same thing for these two guys, because these are co-functions as well. Next thing we're going to do is we're going to take a look at some trigonometric identities. So in trigonometry, we have a great deal of time studying relationships between trig functions and identities, and we pretty much like playing with them. And so we come up with these identities where we say things like sine is always 1 over cosecant, or cosine is always equals 1 over secant. Tangent is 1 over cotangent. So you're given all this list of identities. And then we also have quotient identities where we say tangent is always sine over cosine, cotangent is cosine over sine. So these are the things you already know. And then lastly, we have this identity where sine squared and cosine squared is always 1. So you guys realize this is for any angle theta. So for any angle theta, this identity should work. It's always going to be sine squared plus cosine squared equal to 1. Because sine and cosine are always ratios, it will always work. And then similarly, 1 plus tangent squared is always secant squared, and then 1 plus cotangent squared equals cosecant squared. So if you're curious about how these identities are formed, feel free to take a look at more details in the textbook, or feel free to find some other resources, but I'm not getting into details. So let's take a look at an example and see how we can apply trig identities. So here's an example where we have theta to be an acute angle such that sine of theta, so we're given the sine value, which is 0.6. Then we're going to do find the values of cotangent and tangent using trig identities. So because we know the relationship between sine and cosine, it's always going to be sine squared plus cosine squared equals 1. And because we're given the sine value, so you guys realize we have sine theta to be 0.6. So what I'm going to do is I'm going to use that into this equation where we square the sine and then square the cosine and get 1. So that we do that, and then 0.6 squared, we can move that to the other side, so then we can isolate cosine, then cosine squared because 1 becomes 1 minus 0.6 squared, which is 0.64. We take the square root of both sides to cancel out that square thing. So square root of 0.64 is going to be 0.8. And so that's going to be my cosine value. Now I need to find my tangent, which is the next component of the question, you may remember. So to find tangent, I'm going to do sine theta divided by cosine theta, and then because sine is 0.6, cosine is 0.8, it's always going to be 0.71. So we can use these results and basically write out the right triangle, right, like in the figure, where we have any theta given, then opposite is 0.6 because that was my sine. The adjacent here, this one is adjacent, this one is opposite. Adjacent is 0.8, and then using these ratios, we can come up with the hypotenuse, which is going to be 1. Next thing I'm going to show you is going to be a couple of application problems involving right triangles. So many applications of trigonometry involves a process called solving right triangles. So in these types of applications, you're generally given one side of a right triangle, and generally you're given an angle, and generally asked to find the other side. You may have seen these problems before. I'm going to do one on this video where it's coming up pretty soon. But generally, you're either given a side or an angle, or sometimes you're given two sides, and then you're asked to find the angles. So that's kind of the process. So like you're going to be generally given some angle, and then you're going to be given like say side lengths like x and y. You're going to sometimes be given that. Depending on the situation, you're going to be able to use it. And because we know that ratios are always fixed, so like no matter what angle you're given, sine theta is always going to be equal to whatever hypotenuse this is. So it's going to be y over hypotenuse, right? So it's always going to be the same ratio. We're getting to that detail. That example 8 is coming up pretty soon. But here I like to show you guys, in some examples, you may be given the angle of depression, which is what we call like a thing, an object that has below the, like say, sea level or your observation level. We call it angle of depression. So that is kind of like a negative angle, like negative direction angle, is commonly used in some application problems. And then this is generally angle of elevation, which we have like a positive angle, positive direction angle, or counterclockwise, and then the other one is clockwise. All right, let's get into the example 8. So we have a person who is standing 115 feet from the base of the Washington Monument, as shown in the figure below. The surveyor or the person measures the angle of elevation to the top of the monument as 78.3. So you guys realize we have this person, the angle right here seems to be 78.3 angles. Then the question says, how tall is Washington Monument? In other words, we need to find what y is. So you guys can see this is a clear example where we can create this cool right triangle with the angle 78.3. What we're given is the angle, and what else is given is the side length of the adjacent side, which is 115. And what we're trying to figure out is y, which is what we don't know. So what we know here is that because we're given the angle and one side, we should be able to find the other side, which is y, using trigonometry. The way we're going to do that is we're going to take a look at what y is. You guys realize y is the vertical distance, or it's the opposite. And we know what sine function does. Sine function is always opposite over hypotenuse, right? So we know that. And because we know that, we can use that fact, or either we can use sine function, but the problem is I don't know the hypotenuse, right? I don't have the hypotenuse. So what could be useful here is instead of using the sine function, why don't we use the tangent function? Because we know that tangent is opposite over adjacent. And opposite is what we're trying to figure out. Adjacent is what we have, and we can compute tangent theta using our calculators. So that's what we're going to do. We're going to go ahead and write tangent function, which is tangent of 78.3. So this is going to be the input value. So you're going to use that to equate y equals x, y over x. So x will be known because adjacent is given, 115. And y is going to be what we're going to be solving for. So let's solve for it. Then y, you kind of do like a cross multiplication. So y equals x, which is 115, times tangent function. And then x is given 115. And this, again, because values for trig functions are always fixed, they're always ratios, and these ratios are always same. All you can do is you can use your calculator to compute what tangent 78.3 is. When you compute that, you get something like 4.82882. And then that approximately equal to 555 feet. And that would be how tall Washington Monument is. And with that, I'm going to conclude my video.